To study Markov chains, first we look at some definitions, term and notations. In a Markov chain with k possible states, we have a k by k square matrix M, which is called transition matrix, and any entries of this matrix M in i's row and j's column is the transition probability from state I to state j. So we are moving from rows to columns. So states numbers in the row is the preceding or the old state, and in the column we have the new state. But we may have another notation. We use this notation if we have the state vector as a row vector, like the one that we see here in this matrices. Matrix P, or the probability matrix, or the Markov matrix, here is a matrix whose rows has sum equal to 1. So in this case, some row and columns both are 1, but if we look at the other one, like this one, the third one, we can see that in each row we have the sum for the entries is equal to 1. This is the case, as I said, for when we have the state vectors as row vectors. But what do we mean with this 1/2 and 1/2 inside the state vector lambda? This is for an observation. It means that when system moves on and in each observation we want to study the system. For example, this is the 10th observation. In the 10th observation, it says that by probability 1/2, the system is going to be at a state 1, by another probability 1/2 in state 2. So at any observation, let's say nth observation, x is going to be the state vector with k components, and i's component of this xi is the probability that the system is in the i's state at that time or at that observation. The relation between the nth observation and by the next observation, xn plus 1, so by this n inside the parentheses, it's not for the taking to the power, it is just a notation to show that this is the nth step or nth observation. We move on to the next step, or xn plus 1. It depends only to the previous state. So if you want to find the state vector for the next observation, it's going to be xn multiplied by m. And in the long run, this is also an important point that we want to see what's going to happen to the system and whether the system is going to approach to a steady state or not. So what is a steady state or stationary state, equilibrium state, or invariant distribution? First, we define a measure. A measure, in this case a row vector, is a vector with non-negative entries. And a measure is called invariant measure if we multiply it by the probability matrix P and we get the same vector, or it remains unchanged and we call it invariant. And in case that this lambda is a probability matrix, it means that the sum of the entries is equal to 1. We call it invariant distribution or invariant state, steady state, any of these names. So these are equivalent. Here we have some matrices and some states, and we want to check whether they are invariant distributions or not. So if the question arises like this, it means that just multiply this row vector by that matrix and check whether you can get the same lambda or not, or it's going to change. If it's not changing, so it is a invariant distribution. Here I explain one of them. For example, the last one, We said that if we consider the state vector as row vectors, then we are moving from rows to columns. So the old state or preceding state is the rows and new states are in the columns. So from row 1 to column 1, from 1 to 1, here it says that the probability is 3/4. So here I need to write 3/4. So if I want to write 3/4, I can write 0.75. Or if by mistake, if you write 3 divided by 4, make sure that you need a equality sign before this. Because if you don't use that equality sign, it will be considered as a date and it shows that it is 4th of March. And if you now delete that one, that entries or that cell, and this time write equal 3 divided by 4, since the type or data type for that cell has been changed by the previous entry, then again it's going to give you something incorrect. So to get rid of this, you can copy maybe one of the other cells here. Now they have general data type. Now I can write equal 3 divided by 4, which is 3/4. And this one for sure is going to be equal 1 minus the other one, because we said that rows are going to be probability vectors, or the sum of them is 1. So I didn't write 1/4. I know that 1/4 is also 25% or 0.25. And here also I have 1/2, 1/2. So for now I just directly write 1/2, 0.5, and 0.5. So this is the transition matrix. And we want to check whether 2/3 and 1/3, this vector is invariant distribution or not. So if the question asks this one, so you don't need to solve any problem. You just give the same values here. Here I write 2/3 and here 1/3 or 1 minus that one, which is exactly the same. And here we try to multiply matrix M by this vector X and check whether we are going to get the same vector X or not. If we get the same, so it is invariant. It's not changing. So here I need to write equal. We want to multiply a matrix by a vector, or we need matrix multiplication, which is M mult, this function. First, we said that if it is a row vector, we need to multiply it from left. So you should select the row vector first, and then the matrix. Now we can see that, yes, we get the same result. It means that this is invariant. So to verify whether it is invariant or not, just use the M mult once. Now if I change one of them to something else, for example, so this was a probability and this is 1 minus this. Then I change this one, for example, 0.3 or 31, something like this. Then the result is not going to be the same. It means that 0.31 and 0.69, this vector is not invariant distribution. But the previous one was. So if I change to the previous value, you can see that now they are the same. So this is invariant distribution. So to study the next example, we have a digraph, directed graph, which shows that we have 3 states, 1, 2, 3. And we want to first of all show the transition matrix based on this graph. Sometimes we graph based on the given information, but here all the information are simplified in this graph. So it shows that we have 3 states, so I need to write 1, 2, 3 in about the row and next to the columns, about the columns and next to the rows. So, and we know that we are moving from rows to columns. So from row 1 to column 1. It means that from node 1 to node 1. So here we can see that if we are in vertex 1, by probability 1, or certainly, we are going to move to 2. So from 1, we are going to move to 2 by probability 1. And for the others, for sure, we are going to have 0 and 0. So in case that, and this is a robot moving around these vertices, and after every minute, it decides to stay, for example, at 2 or move to 3 by the given probability. So these information are given to the robot, and it moves around, and we want to find out, for example, after 10 minutes, after 2 hours, if it starts from 1, it's going to be at what vertex or by what probability. It can be again at the same vertex 1 or another vertex. We will see the type of questions. For now, we are just looking at the graph and writing the transition matrix. Now, if we are at 2, it says that by probability 1/2, the robot will move to 3. By probability 1/2 from 2 to 3. So here we have 0.5 by probability half. So the sum for the row must be equal to 1. And it doesn't move to the 1. It means that by other 50% probability, it may stay at the same vertex. So if we don't show that loop, it means that if outgoing is the sum of the outgoing vectors is not equal to 1, so the remaining part is going to be from the same vector to itself. So 2 to 2, we have again 0.5. It means that 50%, by 50% probability, it may move to 3, or for the next minute, it will stay at 2 again. Again, another minute, it may again stay by 50% or move to 3. For sure, it's not going to move to 1 by probability 0. If it's in 3, by probability 1/2, it goes to 1. So here we have 1/2. And by the rest, it means that by 1/2, it stays at the same place. Again, this is also 1/2. And this one becomes 0. So this is how to write the probability matrix or Markov matrix or transition matrix based on the graph. So yeah, I put some cycles like this. It shows that if here we have 1/2, another 1/2 should be written above this. It means that it goes from 2 to 2. Or we can put this one also here. If this is here or not, we have the same data, okay, the same information, whether this cycle is shown here by another 1/2 above it or not. Now, we have this matrix, and the question says that if the robot starts at vertex 2, what is the probability that after 5 minutes it will be at vertex 1? Every 1 minute it follows this probabilities and moves around this cycle, and after 5 minutes we want to see where is going to be the position for the robot, or by what probability it's going to be in what state. So the initial state M, it says that it starts at 2, so certainly it is at 2. So here we have 1 and the others are 0. So this is the initial state. For sure we know that it's at vertex 2. So let's write this 1, 2, 3 also there. So these are vertex 1, 2, 3. At initial state it is at 2, so this is 1, the other is 0. But we may have by probability something, it might be at 0, at 1, by some probability at 2, by some probability at 3. But it says that it is at 2, so for sure it's at 2, certainly, so that probability is 1, the rest 0. After 1 minute or 1 step transition, we need to multiply it by the matrix M to get these 3 values. So what should I write here? Here I need to write equal matrix multiplication or M mult of the previous state, but I don't lock this one because I want this previous state to move down, because in the third step or second step, the previous step is going to be the first step, so it should move down. And the matrix, probability matrix or transition matrix, but we should lock this one. I lock it by F4, or I can give a name for that and call the name. I will do the same for the other part. Next time that I want to use this, I will use the name for that. So I lock that, and this is the probability or state vector for the first step or after 1 minute. Since we wrote the formula by locking the matrix and keeping this row number free, then it can move down and we can find the others the same way. Now, what was the question? After 5 minutes, by what probability is going to be at vertex 1 or at state 1? At vertex 1, this is the answer for that. So the solution is going to be 0.1875. So the answer is this time. This is the answer for part A of this question. And also we want to find out what's going to happen in the long run. Find the invariant distribution or steady state. And what is the probability that in the long run the robot will be at vertex 3 starting at any arbitrary vertex. It means that it does not depend on the initial state. So for the invariant state, we need to find the vector. If we multiply it by transition matrix M, we get the same thing. And that vector must be a probability vector. So we have a condition here. Here we have sum of these xi's, but I need this sum to be equal to 1. We give some initial value for, we can give anything. We can give 0, 0, 0, but, or 0, 1, 0, any initial value, but it should be probability. This sum must be equal to 1. And here also I write the, again, formula, M mult of X and M. And this is M. We don't need to lock because we don't want to copy the formula. No. If the initial state is 0, 1, 0, then X times M is going to be 0, 0.5, 0.5. This is not the same, so it means that 0, 1, 0 is not the invariant distribution. But what is that invariant distribution? We start to solve this problem. I want to have this sum equal to 1 and also X to be equal to X times M. So we select this cell that I have this sum, and we start again to use solver, but this time we are not minimizing or maximizing. We have this cell, should select this cell, and we want the value of this cell to be equal to 1. Here I need to write 1. This sum must be equal to 1. Changing variables are xi's, these cells, and the condition is we need to have xi's or the x vector to be equal to x times m, this vector. Again, we want to solve with simplex, and xi's are non-negative, and since their sum is 1, for sure they are going to be between 0 and 1. And if we solve, we get this solution. We can see that if x is 0.2, 0.4, 0.4, if I multiply it by m, I get the same thing. But what is the answer for the second part? By what probability it's going to be at vertex 3? So this time the answer for this part is this probability. It means that by 40% chance, in the long run, the robot will be at vertex 3. by another 40% at 2, and by 20% at vertex 1. So it's going to be less probable to be at vertex 1. Vertex 2 and 3 are equally likely to be at those vertices. Now we look at another exercise. This time we have 8 by 8, or we have 8 states. And the question is, we have it's like this. We have a traffic officer. She is assigned to control the traffic at 8 intersections, intersection 1, 2, 3, 4, 5, 6, 7, 8, these intersections. She is instructed to remain at each intersection for an hour. After 1 hour, she should do this way for an hour, and then to either remain at the same intersection or move to a neighboring intersection. So she's not going to follow a specific or a routine way, but by some probability that we will see what probability. So it's going to be equally likely to move to the others or stay. Then based on that, we are going to find the probabilities for this matrix. To avoid establishing a pattern, this is the reason. For example, for the drivers that you're moving there, we don't want them to understand, for example, at what time this officer will be at what intersection. She's told to choose her new intersection on a random basis, with each possible choice equally likely. It means that if it is, for example, at intersection 4, there are 5 possibilities. She can stay at the same intersection for the next hour. She can move to 1, 3, 5, or 7. Since the probabilities are equally likely, or the choices are equally likely, then for each of them, the probability is going to be 1 out of 5, or 1/5. So for intersection 4, we have all this information. For intersection 1, we have 1, 2, 3 possibilities. Then if we have equal chances to stay at the same intersection or move to the others, we start to write the probabilities inside the matrix. So in the first row, we know that the old intersection, we start from row and we move to the new intersection in the column. So from row 1 to row 1. So if we are at row 1, we have 3 possibilities: staying at 1, moving to 2, moving to 4 by the same probability. 3 choices, then we have 1/3 probability to each of them. So 1 to 1 is 1/3. So here I write equal 1/3. And then 1 to 2, again 1/3. And 1 to 4 also 1/3. And the rest zeros, so the others are 0. And in each row, we must have the sum of these values equal to 1, which is exactly the same. Now, if she's at 2, there are 1, 2, again 3 possibilities, but from 2, she can move to 1. So the same probability. I can copy this down, maybe it works, yes. From 2 to 2, she can stay at 2, the same probability. And also she can move to 5. She can move to 5, this can be also 1/3. And the others, 0. If she is at intersection 3, there are exactly the same 1, 2, 3 possibilities, again 1/3, 1/3. From 3, she can move, stay at 3, move to 4 or 6. So I copy this and paste there. So from 3 to 3, she can stay here. From 3 to 4 or 6. And the others, zeros. I could do something else. I could put zeros everywhere and just change those which are not zero. Now I do that one here. I put zeros here and I will change those which are not zero. All of them I copy down. For now they are all zeros. Now we find those which are not zeros. For 4, from 4 we said that we have 5 possible cases. All of them are going to be 1/5. From 4 to 1, 1/5. From 4 to 1, 1/5, which is 0.2. The others also are the same, so I can copy this. So from 4 to 3, also the same. From 4 to 4, she can stay at 4. She can move to 5, and also she can move to 7. If she is at vertex 5, she had again 3 choices to go to 2, 4, and 8. So 2, 4, and 8, so they are 1/3. So from 5 to 2, let's say, no, from 5 we have 4 possibilities. From 5 she can go to 2, 8, 4, or stay at 5. So these are going to be 1/4. So from 5 to 2, 1/4, from 5 to 2, 1/4, or 4.25. 5 to 4, the same. 5 to 5, and 5 to 8. From 6, there are 3 possibilities, again 1/3. From 6 she can go to 3 by 1/3. From 6 she can stay at 6 again, or move to 7. If she's at 7, again we have 3, 1, 2, 3, this time we have 4. So these are 1/4. From 7 to 4, 1/4. 7 to 6, 1/4. 7 to 7 and 7 to 8, also 1/4. And if she is at 8, there are 3 possibilities, 8 itself, 5 or 7, or 1/3. So again, I copy this, 1/3, 8 to 5, 1/3, 8 to 7, and 8 to 8. Now let's check. When we have 1/3 probability, then I need to have 3 of them, 1/4, 4 of them, 3, 4. I can also add this sum and write in another column and check whether we are doing correctly or not. 3, 3, and 3. Now this is the probability matrix. Now for the next time, as I said, I'm going to give a name for this, because I'm going to use all these entries or all these data as a matrix. Then I select them all and try to give a name for that. Then I go to the formula and say I want to define a name. I want to define a name, and I give a name for this M for officer. Okay. Now, next time, I want to use this information to continue. Now, the question says that if the officer begins at intersection 5, it means that certainly she's at 5 at the initial state. It means that this is 1 and the rest are 0. So what's the initial state? She starts at 1. So again, I copy this 1 to 8 and paste here. So at the state 5, initial state is 1, and the rest are zeros. Or I could put zeros everywhere and only a 1 here. That's it. So this is the initial state. After one step, I'm going to multiply the initial state by the matrix. So this time we want to use the name of the matrix, equal matrix multiplication of this initial state, but without locking it, because we want this initial state to move down. And that matrix, we give a name for that. We say that M officer. Matrix for off, you can see this name here because we defined already, and it shows that already selected. And if you define a name, then it's not going to move down. You don't need to worry about the locking the rows or columns. So this is M mod. For the other one, again, I want to multiply by the same matrix. Then if I copy this rule down, it's going to use the previous row as initial state multiplied by another M. Since the previous row was M times capital M multiplying by another M, it's going to be M squared. So if I go down like this, then this is exactly M squared. And if I click on this, you can see that we are multiplying this initial row, which is M times M, by the matrix M, becomes M times M squared, lowercase m, which is the initial state, times M squared, or after two steps. Okay. Now I can again select this row and continue up to the 10, because it says that after 10 hours. After 1 hour she's here, after 2 hours, and then after 10 hours we got these probabilities. And we want to find the probability that after 10 hours she's going to be at what location? What's her probability location? Hour by hour. So in each hour we see, okay, what's happening for 10 hours. For example, what's the probability that she's going to be at intersection 5 after 10 hours? It is 0.14, or any other probability we can give from here. While what probability she's going to be at what intersection. And finally, we want to find the invariant distribution or steady state for this, and also what is the probability that in the long run she'll be at the intersection 4 starting at any arbitrary vertex. But in this case, we consider that every day she starts from the last intersection that she was the day before. Then we can study as a long run, or the time approaches to infinity. If she follows this rule, then we can find out finally by what probability she will be appear at what intersection. Now again the same way, here we have xi's. Again we can give the value, initial value. It can be anything, even if it's not a probability vector, but I give a probability vector. And here we need a formula equals sum for these values that must be equal to 1. For now this 1, but if I give this one 0 also, it doesn't matter. It will be the solver will solve it by that initial state. But for simplicity, or to show that it's a probability vector, I give one of them 1 and the rest 0. And here also the same way, we want to multiply this x and M officer, this matrix. Now we want to solve it. We want to go again to solver. This time we selected this cell. Let me reset again and do it again. So we select this cell and we want its value to be equal to 1 for different values of x1, x2 up to x8 or xij's, and changing variables are these xi's, and conditions, we add a constraint, xi's, this vector must be equal to x times m, means that it's not changing or it is invariant. Now we solve it, and you can see that these vectors, these entries of the vector x is the same as x times m. For this x is the invariant distribution, and for answering where is going to be, or by what probability she is going to be at intersection 4. Intersection 4, we have 1 for is this column. So the answer is going to be this value. By probability, or by 17 or almost 18%, she's going to be at intersection, in the long run, at intersection 4. So we studied 2 exercises, and also I mentioned that all these notations can change if we consider the state vector as column vectors. Then the probability matrices also are going to have different form. We should write the probabilities reading or moving from columns to rows, and the columns must have sum equal to 1.